Hi everyone, and welcome to our discussion on financial decision making under uncertainty. And in this particular video, we're going to discuss about a concept called fair games. And fair games is going to be something that we're going to build our discussion on that stable criterion for making a decision on which investment alternative to take, given that the conditions of the world are generally uncertain. So we're gonna start with our proof on why the expected value criterion, which we discussed in the past video, will fail in some regards because it is not a stable criterion when you look at the bigger scheme of things, when you start to incorporate external things such as wealth, such as preferences and other things. So let's discuss in this relatively short video compared to the other lectures the concept of a fair game. So a fair game, a fair game or a fair bet or a fair lottery, these terms are interchangeable, is a random game. Okay, so it's a random game with a specified set of prices and associated probabilities that have essentially an expected value equal to zero, meaning the expected value of participating in a fair game, in a fair bet, in a fair lottery is equal to zero. So on the average, you leave with nothing. You lose nothing, you gain nothing. And that's essentially a fair game. So for example, this is the most common one. So say you flip a coin with a friend for say $1 or 1 unit of currency. And if that coin turns up heads, you win $1. And if you lose, you lose $1. So if the coin lands heads, if the coin lands heads, you gain $1. So your friend gives you $1. If it lands tails, you give your friend $1, right? And we can calculate, or so we can actually visualize in our head already the probability distribution function of X, right? And the way that we do that is we're going to have three columns, or a PDF could be a table by definition. It could be an equation, a table, or in words. So in this case, let's use a table. So we have two states of nature. So these are your states of nature. And we have two because there are two sides to the fair coin. So you could either land heads or you could either land tails. It just so happens that if you land heads, you win. If you land tails, you lose, right? So you have two states of nature in this particular game. Now, if it's a fair coin, as we know, and we toss it without any form of bias, the likelihood of it being a head or a tail is exactly the same. Meaning the probability that the coin could land head is 0.5. The probability it could land not a head, which is tails, is also 0.5. And note, the probability column must sum up to 1. Okay, so if you add 0.5 and 0.5, you leave with 1. Now, VOP, it stands for value. So this is value of the payoff, right? This is the value of the payoff. It just tells you the monetary value associated with the investment at a given state of nature. So what does that mean? If the coin lands heads, i.e. state 1, you earn a unit of currency. You earn a peso, you earn $1. But if it lands on tails, you lose $1. So that's minus 1 peso, minus 1 unit of currency. Then the way that we get the expected value, well, the expected value of X or the event is just equal to the probability, okay, it's just equal to the sum of the probabilities multiplied to the value of the payoffs, right? To the value of the payoffs that we have. So we have the first state of nature, that's 0.5, multiplied to the payoff potentially at the first state of nature, that's equal to 1, plus the probability of the second state of nature, that's 0.5, times the payoff at that state of nature, which is -1. And of course, this should be obvious. This is 0.5 minus 0.5, and that's equal to 0. And this is essentially what constitutes a fair game. We have an expected value, monetary value or payoff equal to 0. Okay, so that's a fair game. That's what constitutes a fair game. So this is just me restating it in the presentation that we have. So the expected value of the game is 0. Now, for example, you were presented, I modified the game a little bit. Instead of you gaining just $1 or a peso when you win, i.e. when the coin lands heads, I give you $10 or 10 pesos. But if you lose, you just have to pay me $1. Okay. Now, that's just a slight modification, but it makes this particular game no longer fair. Why? Because the expected value of the game is no longer 0. In fact, it's different. It's gonna be 4.5 because if the payoff that you have, given that the probabilities of it being a head or a tail are equal, the payoff that you have are now different. So if we get the expected value of this, the expected value of x would be, for state 1, that's 0.5, that's the probability, times the payoff, which is 10, plus 0.5, which is the probability of state 2, minus the loss, which is -1. 0.5 times 10, that's 5. 0.5 times -1, that's minus 0.5. Therefore, the expected value is 4.5, which is not equal to 0. Therefore, this particular scenario is not a fair game. Now, how do you solve this? How do you make an unfair game a fair game? Well, it's simple, really. If this is the expected value, which is 4.5 units of currency, 4.5 pesos or dollars, you can make it 0 again, okay, essentially 0 again, by fixing an entry fee, right? So for example, so this is a gamble. In order for you to even partake in the gamble, so suppose you want to keep these, you want to keep this matrix, this structure or this reward system, you just charge the person 4.5 pesos or 4.5 units of currency to even play. If they don't pay that, then they can't play the game, right? And when they pay that, they can play the game. And if they pay that entrance fee and they end up winning, they win. If they end up losing, then they lose. But the expected value of the overall scenario is now going to be equal to 0. So that unfair game can be made fair. And you can see this in a lot of casinos or some gambling establishments worldwide. So let's discuss a little bit more on the intuition behind the fair game. And we're going to stop here essentially for this particular lecture. And what we notice is that it's long been observed and recognized that most people would not prefer to play fair games. Well, if you look at the scenario we had earlier, you might think, oh, I'm willing to play that game. Sure, right? Because the payouts that you, what you would spend and what you would risk is such a low amount. It's $1, 1 unit of currency, $10, 10 units of currency. That's nothing. Right? That's nothing to most people. But what if I took up the odds? Actually, I'm not taking up the odds. I'm just going to increase the bet. What if I ask you to play that same game, but instead wager $1 million, 1 million units of currency, and you still have that same sort of structure? If it lands heads, you win $1 million. If it lands tails, you lose $1 million. Some people would not be willing to play that game anymore because they think that the risk is so high. But then in reality, the risk didn't change at all because the expected value of the game is still 0. Right? So there was no change in risk at all. All you did was increase the betting amount, right? And in general, right, what we observe is that when we increase these amounts, there are a portion of the population that would generally hesitate or pull back from playing this same game, right? Because they don't want to risk that much money. But in fact, the risk didn't change. And one of the very first mathematicians to study these reasons for their unwillingness to engage in fair bets is Daniel Bernoulli in the 18th century. And in particular, he coined this term and he sort of postulated this term called the Petersburg paradox, which we will discuss in the next video. So I hope you enjoyed this video on fair games, and I'll see you in the next video. Thank you for your attention.